Sorry.
I think it's working. Yeah. Hi, everyone. First of all, thanks a lot for to the organizers for making this nice workshop happen. And this is my first time joining a workshop in person that I travel to since all the craziness started a few years ago. So yeah, very nice to be here in person, meeting some people that I knew from before and some new faces as well. So I'm going to talk about automated lens modeling when we will have thousands of new lensing systems discovered by the Rubin Observatory LSST. So we have already heard a few talks based on this goal. So I'm going to describe a slightly different approach from the previous talks that were given. So for the first part of my talk, I'm going to talk about what kind of science that we would like to do with these strongly lensed transients from the LSST. So it's the time delay cosmography. So we want to measure Hubble constant and other cosmological parameters with the strongly lensed transients. And for the second half, I'm going to describe my roadmap to get to an automated modeling pipeline that can help us handle these very large samples of lensed transients. So already a few talks have given the introduction to time delay cosmography. So I'll be very brief, just in case there are some people in the Zoom that joined right now. So here is the usual schematic of a strongly lensed system where we have a foreground galaxy and a background quasar being strongly lensed into multiple images. And so in this case, we have the three angular diameter distances between the three pairings of between the observer, the lens galaxy, and the background source. So now there is a time delay between the arrival time of photons that were emitted at the same time from the background source. And if we monitor the brightnesses of the different images, then we can find similar features in the light curves that are lagged. So in that way, we can measure the time delay. So that's the delta t here. And then if we divide out this term, which is the pharma potential difference or a lensing potential difference, then what we are left with is a geometric term that only depends on cosmological distances. And that's how time delays gives us a measurement of cosmological parameters. So now you can see this pharma potential difference basically comes from how mass is distributed in the lensing objects, so the foreground galaxy. And so to get to this term, we need to model the mass distribution, so which will be the main point for the remainder of my talk, how we model the mass distribution in lensing galaxies. So as you have seen already in a few different talks, that the Holy Cow collaboration has been famously working on this method. They have done 6 systems, and then their Strides collaboration did a new measurement on the 7th time delay lens system. So now these different collaborations, Holy Cow, Sharp, and Strides, now they're combined into a broader umbrella collaboration called TD Cosmo. So these are the 7 lens systems that have been analyzed so far, and these what you have seen already, or another version of it. So that gives a combined measurement of a 2% measurement of the Hubble constant just from strongly lensed quasars. And in this plot basically shows where it stands in the recent Hubble tension or the debate, showing that it agrees very well with the cosmic distance ladder based on Cepheid collaboration measurement from the Shoes team. So now to settle this debate, what we want is a 1.5% or better precision in Hubble constant measurement from a completely independent method like time delay cosmography. So now this is a 2% measurement. But this measurement depends on a very specific assumption on the mass profile, which is assuming that the mass in the lensing galaxy is distributed as a parallel. So now let me briefly describe a well-known degeneracy in lensing, which is called the Marshall degeneracy, and how this assumption and the Marshall degeneracy can potentially bias the Hubble constant measurement. So this is a qualitative explanation of how Marshall degeneracy works in lensing. So if we take the density profile to be a parallel, so if in the log-log plot of density versus radius, it would be a straight line. And this kind of model fits very well to the imaging data that we have in instrument lensing. And also this is motivated by previous observations from non-lensing observations. For example, stellar dynamics of local elliptical galaxies and X-ray intensity observations. All of those different data are very well fitted by taking the galaxy mass distribution to be a parallel. So this is empirically motivated, and we do not have any reason to think more complex than this. So now there is a mathematical transform that we can apply on this mass distribution, which will make the mass distribution to look like a little different. But this mathematical transform keeps all the imaging observables invariant. So this new mass profile will also fit our imaging data equally well. However, in this transformation, the unknown source position changes, and it also changes the potential difference. And then the resultant Hubble constant that will come out of this new model will also be different. So now, but this is not a parallel model anymore after we have applied the Marshall transform. So if the unknown truth about the mass density profile has some deviation from the power law, then it can potentially bias the Hubble constant measurement from time delay cosmography. So because of this, we decided to relax this assumption and see what we get and constrain the shape of the mass density. So if it's a power law or if there is a deviation, so the shape of the mass density profile using non-lensing observables. So in that way, these extra observables can break the Marshall degeneracy. So, so this is a summary of that in work. So starting from the top, so this is the first measurement, assuming a parallel mass profile for the 7 time delay lenses that gives a 2% measurement of the Hubble constant. So now if we do not assume any parallel in the lens model and only allow stellar dynamics to tell us how the mass profile shape should be, so then you can see the uncertainty becomes much larger to about 9%. So now we want to use prior from other systems, and we only have 7 systems that have measured time delays. So we can use other lensing systems that do not have time delay measurements, but still you can use their lensing and dynamical observables to give us a prior on the mass density profile slope. So that's what is done for these last 2 points, where a sample of SLAX galaxies are used as a source of prior for the time delay lenses. And with this prior, the uncertainty decreases to 5%, but also it shifts towards a lower value, interestingly, very close to the Planck value. So there is an assumption here too. The assumption is that the SLAX lenses are from the same trend population of the time delay lenses, which may not be true because the mean redshift between these 2 samples are quite different. So the time delay lenses have a mean redshift of 0.6 and SLAX lenses have a mean redshift of 0.2. So yeah, so this is an illustration of the current status of time delay lensing measurement of the Hubble constant based on different levels of assumptions. So this is a quick summary slide for the forecast that we can get to with a larger sample of tiny lenses with these non-lensing observables that can break the Marshall degeneracy. So just quickly, a sample of 40 tiny lenses with specially resolved kinematics to help break the Marshall degeneracy can get us to close to 1% precision. So we need to do better than 1.5% to settle the recent Hubble tension at a 5 sigma level. So another way to break the Marshall degeneracy is to use, if we know the unlensed source brightness, which we can, if the strongly lensed source is a type 1a supernova. So in that case, the unlensed source brightness, which can be standardized, we can use that to break the Marshall degeneracy. And this forecast shows that after 10 years of LSST observations, we will get to below 2% uncertainty in a Hubble constant. It's close to 1.5 here. So this workshop is for transients. So that's why I highlighted the science case with transients, but without, there is also a lot of lenses that are that just have a galaxy as the source. So these are galaxy lens systems. And there is also a lot of astrophysical applications for these kind of systems. So there are forecasts that we'll have about 10,000 new galaxy lens systems discovered from including LSST and the other larger sky surveys that are coming up in this decade. So this is just an illustration of some new lenses that were discovered in the DES survey. So the main point that I want to highlight is that there is a lot of new systems going to be discovered, and we need to model all the systems to use all of this new data. And for that, we really need an automated system to make this modeling process efficient. So these are just to give you a few examples of what kind of models I'm talking about. So the type of modeling that I want to do is not based on LSST data, but imaging data that are of the quality of space telescopes. So one example of would be LSST strongly lensed supernova that have follow-up imaging from HST or JWST. Or that there are in the footprint of Euclid or Roman space telescopes, or strongly lensed quasars with LSST time delays that are in the footprint of Euclid or Roman space telescope, or can have follow-up imaging from HST. So, and the reason is that to really constrain the lens model parameters to the precision that we want, we need high resolution imaging with a very stable PSF. So this is one nice advantage of having a strong lens supernova over a strong lens quasar is that after the supernova fades away, we only end up with a galaxy lens system. And here we see more of the arc, not outshined by the bright supernova. And so this helps in the lens modeling, and actually Ding et al. Show that the lens model constraints improve by a factor of 4 if we have follow-up imaging after the supernova fades away. So just to give a very quick summary of how lens modeling works in the conventional way, which is based on a likelihood. So given the imaging data, we make a model. So in the model, we have to describe how the source galaxy light is distributed. So here you see 3 source components, and how the lens galaxy's mass and light is distributed. So here it's showing the projected surface mass density of the lensing galaxy. There are 2 here. And we also need to know PSF. So given these model components, then we can reconstruct or simulate the observed data. And basically we optimize the likelihood function using the data and the model-based reconstruction to find the best fit model parameters and their uncertainties. So basically we run an MCMC method using this model. So however, this is very time consuming. um, for a human modeler, because in many cases, this model has to be tweaked and improved, and that is already time consuming for one single system if done by a human. So if we want to model 1,000 lens systems in this way by a human, it would take a long time. So, okay, before going into the full automation, I would just like to highlight some comparisons between the likelihood-based inference, which is the more traditional way, and some new emerging ways based on machine learning. So in the likelihood-based inference, we build a model for the mass profile. So if you want to have a complex mass profiles like an NFW plus stars, that is already done in many cases using the likelihood-based inference. But with machine learning approach, such complex mass profile hasn't been demonstrated with high success yet. So once we have a model constrained in the likelihood-based way, that can be used for many different science applications, but neural network-based applications are very fine-tuned and often for one single science case in mind. So if we want to apply the neural network for a different science case, then in many cases, retraining or a different kind of network architecture may be necessary. However, likelihood-based inference is very time-consuming for one system. Apart from the computational cost, it's also already time-consuming for a human, but machine learning approach is very fast. So what I'd like to highlight is that there are two different regimes where these two kinds of modeling approach can be advantageous. So the likelihood-based inference is advantageous for a smaller sample of lenses, and I would argue this number is about 1,000, where this smaller sample is very interesting, more interesting than your average strong lensing system. And machine learning approach is suitable for when we have very large amount of data, and for this very large number of gravitational lens sample, most of them will be very average. So these two are complementary regimes. Okay, so I see these two approaches to be complementary to each other, where the likelihood-based inference can still be very valuable for a smaller sample where there is a lot of intricacy in the lensing system, whereas machine learning approach is really essential when we have like sample size that are more than 10,000 or so. And it's also interesting that machine learning can calibrate its output using the outputs that we get from likelihood-based inference techniques. So this is an example of how we can get to an automation in the likelihood-based inference. So, so this shows a decision tree-based algorithm. So I'm not going to explain all of the different things that's written here, but just to give you an idea, so a decision tree takes the data and then goes through different nodes in this flowchart to decide what is an optimal model. So basically, this whole flowchart decides on a model that is sufficient enough to capture all the details that we see in a lensing system. And when it's decided that, then it runs MCMC, and then we are done. So this was done in a paper led by me back in 2019. Recently, Schmidt et al. Have made an improved version of this same workflow. So this is an illustration of how such a decision tree-based framework can do. So on the odd number columns are the data from HST, and the even number columns are the model-based reconstruction that are done in this automated way. So you can see they look very close. The model looks very close to the data. So, but the decision tree still needs some bit of human input. So it's not fully automated. I would say it's semi-automated, because the decision tree still needs some inputs from a human, and the inputs are like this. So given an image, where is the central deflector? Where are the images? So for example, here, where are the 4 lens quasars? Are there additional source components? So in this system, there are these additional sources. So these, like, apart from the 4 lens quasars, you see there is a doubly imaged arc here, and there is even a third fainter arc there. And are there additional lensing objects? So there is another smaller galaxy here doing lensing. So these are visual recognition tasks. So this is very hard to do in a decision tree, but a visual recognition can be performed using machine learning techniques. So my idea is to have a hybrid approach to reach to full automation. So machine learning can perform visual recognition on a given image, and then visual recognition will provide information to the decision tree to make an optimal model for likelihood-based inference. So this is an example of a neural network that we have built. So this is a UNet, which given an image with HST quality. So this is a simulated image from the evaluation set. This is true label. So this is what we train with, and this is what I get out of. So you can see the different labels. So basically, what kind of object, what object a pixel primarily belongs to is the label. So different coloring points to a different class. The output is not very good, but we do not need it to be perfect. We just need it to be approximately right. So as long as it can tell us where the center of the lensing galaxy is and where the lens quasars are, then it's good enough to provide that information to the decision tree. So yeah, so this kind of task in neural network is called semantic segmentation. But we are still working on it. So in the future, we want to, so this is the simplest case of a lensing system, but we want to upgrade it, this network to also detect nearby perturbers and secondary source components. So the automated pipeline that I'm building based on this hybrid approach is called Dolphin. But Dolphin actually uses Lenstronomy, which is a lens modeling software, and you have heard about Lenstronomy already in a previous talk today. And Simon Vera is the lead developer of Lenstronomy. So Lenstronomy is very powerful, but it's because it's powerful. It has a lot of knobs that you can tune. So what Dolphin does is streamlines all of that process. So the idea is to just provide Dolphin reduced imaging, and Dolphin will act as an artificial intelligence, just like a human modeler, to use Lenstronomy and give you an optimized lens model. So yeah, the main modules of Dolphin is, the first is visual recognition done using machine learning, and then it constructs a model using decision tree, and then it sends the task of model optimization to Lenstronomy, and also uses MCE, but there are also other MCMC samplers that you can use. So this is an example of some models that was done in this way. So this is, again, the odd columns are data, and the even columns are the model reconstruction by Dolphin. So yeah, I've been building this this pipeline in collaboration with Chini Tan, who is my graduate student colleague at Chicago. So some short and long-term goals for Dolphin. So we have been testing the capability and fidelity of Dolphin with archival imaging of HST archival imaging of about 150 galaxy lens systems. So when that's done and Dolphin is fully developed, these new models will be used to study galaxy properties and evolution. So the elliptical galaxies here. And then as new lens samples are publicly available, then we'll add it to this master repository of Dolphin analyzed lens systems. It's open source and publicly available on GitHub, but the main idea is that it will be fully ready in time when we are going to have these new discoveries from Rubin, Roman, and Euclid observatories. So that's my talk. So this is the summary slide. I will leave it here. Thanks a lot for listening, and I'll happy to take questions.
Thanks for the nice talk. All right, questions for the speaker.
Yeah, nice talk. Well, that was a lot unexpected. Back on it was like halfway through, you talked about, you know, the improved constraints for lens modeling after the supernova fades away. And that's something that I think, you know, lens supernova people, we've sort of said that for a while without a lot of hard evidence, just like seems like it makes sense. So this is cool. And I was just wondering if on that constraint, is it done with, you know, with the lens supernova without, and then combining the constraints, or is it actually found that like it's better to have no lens supernova positions at all? You know, is it a joint constraint that's the improvement, or it's really absent that's best?
So on that, I don't clearly remember if it's total, but having the point source positions definitely helps in the lens model. So that this is just extra information. But the improvement of factor by 4, I do not clearly remember if it's just from the image without the supernova or combining the second image with the point source positions. So, but I can get back to you. Okay. So it's a combination of both then.
Yeah, very naively, and thanks, great talk, great work. Very naively, how do you generate your visual inspection map to feed your machine learning algorithms?
Right. So like when we're simulating, we know the flux coming from each component. So we basically have kind of like an ad hoc way to say what percentage coming, like setting a threshold. If better than this threshold comes from the quasar, we'll set it to a quasar pixel. And then we like look at the labeling and see if it's right. But this is a very adequate way to do it. But again, we don't need to be perfect here. We just need it to kind of do something okay. Yeah.
Okay, so let's thank the speaker again. So we'll